Hello students, welcome to FosterJEE. This is our third lecture of electrostatics. Till now, we have discussed some basics of electrostatics, Coulomb's law, electric field, and we were on electric field due to different shapes. Till now, we have completed electric field due to point charge and uniform ring. Now, we are going to discuss our third shape, that is electric field of a line charge. First of all, what is a line charge? Suppose we have a very long now long means it has very small thickness, very small thickness. Let us suppose this is T and this is spread over a span of L. So if T is very small than L, then it will be considered as line charge. Now, if this line charge is placed symmetrically, then we have to calculate electric field due to this line charge at a point at a distance x from this line charge and perpendicular to it. Now this distance is x. Here we are also given that a total charge of q is present on this line. So we have to evaluate the value of electric field due to this line charge at this point. As discussed earlier, since this is not a point charge, this is a distributed charge, so we have to take the help of integration. Now we will draw some other diagram. If this is our, then now suppose this is our diagram. Suppose at any distance r, or s, let's take it as s, we take up a small element. What will be its thickness? That will be ds. Now we have to forget about all this rod and consider only this element. What is the distance from this element to the point of concern? From Pythagoras, if this is x, this is s. So our distance, suppose this is y, then y will be x square plus s square, y square. Now the net force between any 2 point charges is given by Coulomb's law. But now here we need electric field, so we will write small electric field dE will be k q. Let's suppose its charge is dq, k dq upon y square. Now the value of y square is x square plus s square, so it becomes k dq upon x square plus s square. Coming to the charge dq, we are given that q is distributed over L length. Hence, L length contains q charge, 1 length would contain q upon L charge, and hence ds length would contain q by L into ds charge. Hence, the value of dq is q upon L ds. Substituting, we get dE as k q by L ds upon x square plus s square. Let's this our first equation. Now, since now only this point charge is present, due to this point charge, the direction of electric field would be away from this point, that is this. And suppose if this angle is alpha, in that case this angle is also alpha. So we have to evaluate the value of, since this is dE, this will be dE cos theta. This is dE cos alpha, sorry, and perpendicular to it, it becomes dE sin alpha. But by symmetry, we can say if we take similar element at a distance s on downward side, it will act in this direction. And in that way, if this is also alpha, because all are symmetrical, the dE cos alpha component will get add up. But the component dE sin alpha will get cancel out. And hence, the net electric field would be only dE cos alpha. So we will write the net electric field E net would be integration dE cos alpha. From equation 1, we will put the value of dE and it becomes integration kq upon L ds upon x square plus s square. Now the value of cos alpha from this diagram, we can write cos alpha as base upon hypotenuse. So the base is x upon hypotenuse is y. So the value of cos alpha is x upon y. Further, the value of y square is x square plus s square. So the value of y becomes root over x square plus s square. Forget about the signs because we have considered it above. So no need to consider minus sign. So our equation becomes E net equals to integration kq by L ds x upon x square plus s square power 3 upon 2. Now here comes the blunder. Note that here there are two variables s and x. So we can't integrate this equation unless we substitute one variable in the form of other. For that, let's go to diagram. We need one single equation which will represent both these variables. So suppose we take the help of tan alpha. The value of tan alpha is perpendicular upon base, that is s upon x. Now the value of tan alpha is s upon x, which gives the value of s to be x tan alpha. Now we will put the value of s in terms of x. So this becomes E net to be integration kq by L x ds upon x square plus x tan alpha square whole power 3 upon 2. So our E net becomes integration kq upon L x ds upon x square common 1 plus tan square alpha whole power 3 upon 2. Note that x square to the power 3 by 2 is x2 into 3 by 2, which is x cube. So this x square will come out as x cube. Writing this, we can write E net as integration kq upon L x cube 1 plus tan square alpha whole power 3 upon 2, and the numerator was x ds. Now we know that identity that 1 plus tan square theta is sec square theta. So we will substitute the value of 1 plus tan square alpha as sec square alpha, which becomes integration kq upon L. This becomes ds upon x square into sec square alpha whole power 3 upon 2, which becomes integration kq upon L ds upon x square sec cube alpha. Now again, this equation has three variables, that is alpha, x and ds. Now we have to change ds in form of x and alpha. Let's see how we will do it. Again, from this equation, s equals to x tan alpha, s equals to x tan alpha. Differentiating this equation, we get ds as, this side becomes x times differentiation of tan alpha, that is sec square alpha, and also d alpha will come. Evaluating this integral, we will get E net equals to kq L upon Lx. The integration of cos x becomes sin x, or cos alpha becomes sin alpha. So this becomes sin alpha from alpha 1 to alpha 2. Let's see what are alpha 1 and alpha 2. Alpha 1, alpha 2. This integral becomes E net equals to kq upon Lx sin alpha 2 minus sin alpha 1. This in itself is very important result. So we have to keep in mind this result also. But now we will put the value of sin alpha 1 and sin alpha 2. From this diagram, we can see we have taken initial limit as alpha 1, which is the angle from this point to this part of rod, and this is our alpha 1. So if this is L, this half length will be L by 2, and the value of tan alpha 1 will be L upon 2 by x, that is L by 2x, the value of tan alpha 1. Since the value of tan alpha 1 is L upon 2x, we can write the value of sin alpha 1 will be L upon 2 upon root over L upon 2 whole square plus x square. Now this is our sin alpha 1. Similarly, sin alpha 2 will be from this part of rod to this point, and in that case sin alpha 2 will be L upon 2 upon root of L upon 2 whole square plus x square, since it's symmetry. But note that in these terms we have to take alpha 1 as negative and alpha 2 is positive. Why? Because since this is our reference phase, if this is our reference line, so we can see above this line alpha is positive and below this line alpha is negative. So the limit is minus alpha 1 to plus alpha 2. So we will change this a bit. This becomes minus alpha 1 to plus alpha 2. This minus alpha 1 to plus alpha 2, this becomes alpha 2 minus sine of minus, which becomes kq upon lx sine alpha 2 plus sine alpha 1. So putting the values, we can write E net as kq upon lx sine of alpha 1 plus sine of alpha 2. Since both are same and both are adding, this becomes 2 times of L upon 2 root over L upon 2 whole square plus x square. In short, we can write E net as 1 upon 4 pi epsilon naught q upon lx into L upon root over L upon 2 square plus x square. So this is our resultant electric field. We can also cut these terms and this becomes even more simplified. Now this result is also important, but this result is easy to remember also. This result. Now we will do a small problem based on this. Suppose there is a thin rod. We are supposed to find electric field at a distance 1 meter. At a distance 1 meter. And we are given that this is not symmetrical. This angle is 45 degree and this angle is 60 degree. We can mention it. This angle is 60 degrees and this angle is 45 degrees. We have to find electric field in this direction, that is perpendicular to rod. Electric field perpendicular to rod. So since we are given angles, we will simply use this expression of electric field E net. Remember that in derivation we have derived only electric field perpendicular to the rod. So the expression is kq by lx sine of alpha 1 plus sine of alpha 2. Also, let us suppose its length is L. This is just to illustrate something. So our electric field becomes, suppose a total of 1 coulomb charge is present on the surface. So it becomes k into 1 upon L into x is 1 meter. Now sine of alpha 1 is alpha 1 is this, that is 1 upon root 2 plus sine of alpha 2, that is 60. It becomes root 3 upon 2, that is k by L 2 plus root 6 upon 2 root 2. This is the value of electric field. In short, one thing I would like to mention, that if we are given this rod in terms of angles, that is final angle and initial angle with respect to the point of concern is given. So we will use this expression of electric field. But suppose we are given the length of wire or any rod. In that case, we will use this expression. And we can also evaluate the value of length. Now, what will be this distance? Using tan 60, we can write tan 60 degree as y1, suppose this is y1, y1 upon 1. So y1 is tan 60 and that value is root 3. That is y1 is root 3. And what is the value of this? This is 1. The value of tan 45 is 1. So this becomes 1. So we can put L also to be root 3 plus 1. Hence we can see if we are given only the distance on which electric field is calculated and the angles, we can simply use this expression and formulate our electric field. Moving forward, now suppose we are given that this rod is infinitely long, that is, this rod is infinitely long. Then we have to calculate electric field at a distance x. Now, if the rod were of this length, then theta 2 will be this and theta 1 will be this. On increasing the length, the angle also increases. Now, suppose the length becomes infinite, then in that case, it will become more steep. And finally, at infinity, the angle becomes like this. So we can write at infinity, the angle would be alpha 2 equals to alpha 1 equals to 90 degree. Hence, our expression of electric field was kq upon Lx sine alpha 1 plus sine alpha 2. Now, since L, that is length, is tending to infinity, we can separate q upon L into k upon x. Now, the value of sine alpha 1 and alpha 2 will be sine 90 plus sine 90. That will be 1 plus 1. Now, note that if q charge is distributed over all this surface, infinite surface over infinite length, then the q also is infinite and the length is also infinite. So this becomes infinite upon infinite. But we know, we are given that there should be some unit linear charge density, and we define lambda as linear charge density, which becomes total charge upon total length, which is constant. So in that case, our net electric field will becomes lambda k upon x into 2, or else we can write 1 upon 4 pi epsilon naught lambda 2 upon x. So net electric field will become lambda upon 2 pi epsilon naught x, which is again a very important result. Now, we have to know 2 points. We can use this expression only in 2 cases. Only in 2 cases. First point is either the length of wire or rod is infinite, or the second case, x is very close to the rod. That is the charge or the point. Point is very close to the x. That is, x is very less than L. And this becomes L is very greater than x. They both have different application in different cases. Suppose the first point is clear that the length should be infinite, and in this case we have illustrated this also. But illustrating this second point, we can say if there is a thin rod of some finite value of thickness. That is, it has some finite length. But we are given that its length is, suppose, 10 meters. And we are asked electric field at a point 1 millimeter away from this rod. In that case also, since we can see 1 millimeter is 0.001 meter, which is very less than 10 meters. So in that case also, net electric field will be lambda upon 2 pi epsilon naught r, where r is the distance, that is 1 millimeter. So we have to keep this also in mind. Now this completes some of the important shapes due to which electric field is determined. Coming to our next topic, which is electric field lines. Electric field lines. Now this is already being discussed, but to elaborate, we will discuss here also that these are the imaginary lines which are drawn so that the tangent at any point on the line gives the direction of electric field. Now we have to recall that we have taken one positive charge and one negative charge. Then electric field lines were originating from positive charge and traveling towards negative charge. So this is the representation of electric field lines. So we can say we have already discussed this, that it emerges from positive charge and terminates on negative charge. Now these lines have some special properties which we will discuss now. Properties of electric field lines. First is the tangent drawn at any point on the line gives the direction of electric field at that point. Suppose these are our electric field lines. So we are asked to find the direction of electric field at this particular point. So what we will do? Simply draw a tangent, and this tangent will indicate the direction of electric field. If we draw the tangent at this point, the direction would be this. This point, the direction would be this. So this is the meaning of first point. Second point is electric field lines always begin from positive charge and terminates on negative charge. Negative charge. This we have already discussed. Third point is number of electric field lines originating from a charge in bracket or terminating is proportional to the strength of charge, or else we can say the magnitude of charge. This means suppose we have 1 microcoulomb charge and 1 millicoulomb charge. We know in 1 micro is 10 to the power minus 6 and that is 10 to the power minus 3. We know 1 millicoulomb is greater charge. So we can conclude that number of electric field lines from 1 millicoulomb are greater than 1 microcoulomb. This is the meaning of our third point. Coming to our fourth point, two electric field lines can never intersect each other. Now, suppose we have one charge and it has created some electric field lines around it. Now we take up another charge. It also has some electric field around it. Now, the point says it can never intersect each other. In previous lecture also, we have discussed that when two charges come closer, their electric field interact with each other. Now, this is different from the fact that in that case we have just discussed the interaction. The truth is these will never be like this. So in this way they arrange themselves so that they never intersect each other. Now, what if they intersect each other at any point? So, as we have discussed earlier point that the tangent at any point gives the direction of electric field. But at this point, since it's intersecting, there will be two tangents possible. So, can we say the electric field at this point has two directions? But the property of vectors says that vector quantity has only one direction at a time. Hence, it's not possible. So, it's true that two electric field lines can never intersect each other. Our fifth point is electric field lines can never form closed loops. That means, suppose if this is our charge, this can't happen that electric field line is generated from this charge and then again terminated on this charge. This is never possible. it's always that it will be originating from positive charge and terminating on negative charge. This was the meaning of fifth point. Our sixth point is intensity of electric field strength is proportional to number of electric field lines present in a particular region. Suppose we have a region. For example, in this region we have 2 points, point A and point B. We can see near point A the lines are closely packed with each other, that is, the distance is less, and at B point they are more spaced, and hence we can say electric field intensity at A is greater than electric field intensity at B. Our seventh point is at the region where electric field is absent, electric field lines can't be present. That is, if in any space like this we are given that the net electric field is 0 inside it, we can't have any electric field line present in this region. Electric field lines will be present outside this region, but they can't be present inside. Now, our eighth and the last point is electric field lines travels from higher potential to lower potential. Now, what is the meaning of higher potential and lower potential? That we will discuss in upcoming slides. Now we'll take up a simple problem based on electric field. The question says, a charge Q equals to -2 microcoulomb is placed at origin. We have to find electric field at 3 meters, 4 meters, 0. That is a plane or a point in XY plane. Now, always remember such types of questions in which we are given coordinates on which a value or a quantity has to be evaluated, we should use vector form of equation. And for more such practice problems, please download our app from Apple Play Store or Android Store. Now let's solve this problem. But initially, let's look up in note about vector form of electric field. Vector form of electric field. Electric field. Since electric field is given by k q upon r square. This is the electric field due to any charge q at a distance r. Now, we know this is only the magnitude. But we know, since electric field is a vector quantity, any vector quantity can be represented as the product of its magnitude and its unit vector, that is E cap. Now, if any charge is placed here, Q. Now suppose this is our xy plane and this is our charge, and suppose at any distance r from it, we are asked to find the electric field. Now, this is r. Then what will be the electric field at this point? We can see if this is a positive charge, the direction of electric field would be definitely like this, that is in the direction of r vector. So can we say that direction of electric field is same as direction of unit vector or radius vector? So yes, hence electric field can be represented as vector E equals to magnitude of E into r cap. This is not dot product, just simple multiplication. Also, the magnitude of electric field is this, so we can put in this equation and get vector E equals to kq upon r square r cap. Now, what is meant by unit vector? It's simply, by definition, we can say unit vector is the vector divided by its magnitude. So we will put the value of r vector in this equation. We will get vector E equal to kq upon r square. Vector, the r cap is vector r upon mod r. Note that this is also the magnitude of distance. So these both are same. So this becomes kq by r cube vector r. Hence our field becomes vector E equal to kq by r cube vector r. Now, how will we implement this in our question? Let's see. We are given that charge is placed at origin and its magnitude is -2 microcoulomb. We have to evaluate electric field at 3, 4, 0. So let's draw it in form of diagram. This is our y-axis and this is our x-axis. Y-axis, x-axis. Since our charge is placed at origin, let's say this is charge and this is -2 microcoulomb. Since our final point on which electric field is to be evaluated is 3, 4, 0. That is, this is in xy plane and this is somewhere here. The coordinates is 3, 4, 0. Now, if we will join this point and the charge, this will be the radius vector. And what is the value of radius vector? Is x2 minus x1 vector plus y2, I cap, y2 minus y1 j cap plus Z2 minus Z1 k cap. Now, what is x2? x2 is 3. So 3 minus x1 is, since this is origin, this is 0, 0, 0. This becomes 3 minus 0 I cap plus y2 is 4 minus 0 j cap plus z2 is 0 and z1 is also 0 because it lies in xy plane. So at any point z coordinate is 0. So this becomes r vector equals to 3 I cap plus 4 j cap. Now, in this equation, we can see we have r vector and this vector, which is the magnitude of r vector. So, magnitude of r vector will be r, that will be root over 3 square plus 4 square, which is 5 meters. Now, evaluating for electric field, we can see E equals to kq upon r cube vector r equals to, putting the values, the value of k is 9 into 10 to the power 9. Since it's negative charge, we have to put minus sign, or else we have to reverse the directions. This micro can be written as 10 to the power minus 6 upon, what is r vector, what is r, that is magnitude of r is 5 meters. This becomes 5 cube into, what is vector r? Vector r is 3 I cap plus 4 j cap. Now, solving this, minus 144 3 I cap plus 4 j cap. We can either leave it by this, like this, or we can solve and get 432 I cap plus 576 j cap, and the unit is Newton per Coulomb. So this is our net electric field at 3, 4, 0. And what does minus signify? It signifies that since charge is placed here, the electric field has its direction like this. So either we put negative sign here, or else we just calculate the magnitudes and we just reverse the sign of final electric field. So this is our answer. Now we will discuss one more problem which will help to clear our concepts. The question says, suppose there's a rod whose linear charge density, that is lambda, is not constant and it varies with x. And what is x? Suppose there's a point which is at a distance a from this end of the rod, and the distance from this point to any part of the rod is x, and our linear charge density lambda varies with x as lambda naught x. Hence we can say at this end of the rod, the intensity, that is linear charge density, would be lambda equals to lambda naught a. And if this length is L, the length of rod is L, in that case the linear charge density would be lambda naught a plus L. This is the meaning of lambda naught x. So just remove this. Now we have to evaluate the value of net electric field at this point due to this rod. By now it must be very clear that since every part of this rod is at different distances from our point of concern, we have to use integration. Now suppose at any x we take an element dx. Now by my method, or the method we are studying, we have always said that after selecting an element, just forget everything else and just consider these 2 points. Now, since dx is very small, then this part or this length of rod should behave like point charges. So, what will be the electric field at a distance x because of a point charge, that is dE, because small electric field, that is k dq. Suppose it carries charge dq upon x square. Simple. Now we know linear charge density is lambda is charge per unit distance or unit length. From here we can write dq is lambda dx. Now putting the value of dq here, we will get this becomes k lambda dx upon x square. Now dE equals to, the value of lambda is lambda naught x. So this becomes k lambda naught x dx upon x square, which is equal to k lambda naught dx upon x, which is dE. Now simply we have to integrate this equation. When x was a, that is only this part was covered, so no part of the rod is being covered. In that case, net electric field would be 0. That is, at x equal to a, net electric field will be 0. But when the x becomes a plus l, that is this whole length, then in that case total rod will be considered, and in that case the net electric field would be complete electric field that we need. So final limit is a plus l. Now integrating this equation, we get E net equals to k lambda naught. Now we know integration of dx upon x is natural log x. So using this, it becomes ln x, and the limits are a to a plus l. On putting the limits, we get k lambda naught ln a plus l minus ln a, and we know ln a minus ln b would be ln a by b. So it becomes, this is whole multiplied, so it becomes k lambda naught ln a plus l upon a, and hence we can see E net is k lambda naught ln 1 plus l upon a. This is our final electric field due to a non-uniform rod at a distance a from this end of rod. Now, getting the answer is not only important, but we have to understand how we have derived this equations and how we have arrived at the final solution, which includes application of logarithms, application of integration, etc. and etc. So, in order to tackle an advanced problem, we have to be ready to deal with every concept involving in a problem. So, I am giving you one more problem as homework, and it will be discussed in our next lecture. The question says, we have a rod whose length is L. This length is L. Now, there is a charge Q placed at a distance A from this end of the rod, and a charge Q is distributed uniformly over the entire length of rod. We are also given that this charge is negative charge. Then definitely there would be attraction between these two charges, and also the rod is fixed, that the rod cannot move. Also, it carries total mass m. Hence, due to attraction between the two charges, this charge starts moving towards the rod. Now, we have to find velocity of this charge when it covers half of the distance, that is, it reaches this distance, which is a by 2. Now, we will write this in the form of question, that charge positive Q is distributed over entire length of rod of length L. A charge minus Q, which is placed at a distance A from one end of the rod, and its mass is m. Find the velocity of charge minus Q when it covers half of the distance, that is a by 2, and also rod is fixed. The charge positive Q is distributed, just add one more word here, uniformly. Now, this problem solution will be discussed in our next lecture. And for more practice problems, please download our app from Apple Store and Android Store.